Hello, I'm Andy Briggs and welcome to the Amazing Astronomical Alphabet, a weekly programme in which my Astro Radio co-presenter Daz and I will be talking about anything astronomy related which begins with the week's letter of the alphabet. We'll each choose some things to talk about which are in some way related to the universe, but neither of us will know what the other has chosen. We will then reveal facts about them which are weird, strange, bizarre or simply interesting. Well, welcome back, listeners, to another edition of the Amazing Astronomical Alphabet with me, Andy, and Daz. How are you doing, Daz?
I'm melting. It's so hot.
Britain has a summer. Shock horror.
Yes, this is our week for our summer. So it's due to break this weekend. But then again, saying that, Milton Keynes, they had hailstones the size of golf balls yesterday. So they had a bit of a break in the weather there.
They weren't concrete hailstones, were they?
No, not like the cows.
Like the cows.
The cows in the field. For the people who don't know, it's Milton Keynes is what they described as a new town that they decided they were going to build these towns on this sort of scale. Telford's another one up here in Shropshire. And just to add a countryside feel to it, as you drive in, the fields are full of concrete cows. I haven't been down there for ages, but I hope they've painted them because last time I saw them, they were in a bit of a need of a lick of paint. But yeah, it's just one of those stupid things we do. Yeah. And once you get into Milton Keynes, you never get out.
Well, it's apparently it's easy to find your way around because it was built on the grid system, wasn't it?
Exactly, yeah, exactly. But then they decided to put circular roads around the outside.
Sort of spoils
which confuses the hell out of everybody. Hey, no, I'm only joking. I mean, yeah, I've been through Milton Keynes several times, and it's easy to navigate. But yes, it's the concrete cows and things like that make people chuckle.
Oh, goodness me. Yeah. All right then. Well, as I said, we're back with the Amazing Astronomical Alphabet. We have reached the dizzy heights of G, to boldly go where no Amazing Astronomical Alphabet has gone before. So we've reached the letter G this week, and as you would have heard in the introduction, Daz and I have chosen several astronomical topics to talk about, anything relating to the universe, beginning with the letter G. We don't know what each other's chosen, and that's always the fun, because there's always a possibility we could have duplicated our choices. But so far, we've done pretty well, only duplicated a mere handful, haven't we?
Yeah, exactly. But then again, we've been able to digress in different directions, so that's been a good one. We don't want to jinx it. Touch wood, touch wood.
No. Well, as I think we both found the letter G a lot easier to find interesting material about, a lot easier than F, for example, which was a bit of a struggle. There were a lot to choose from with G, and so hopefully we won't have any duplications, but we will see.
Hopefully, yeah.
We will see. And I believe, Daz, it's your turn to go first this week.
I do believe, yes, it is F.
Off you jolly well go.
Right, okay then. G is for the Great Debate. Open brackets, astronomy, close brackets.
Right.
Now, I should really actually say it's not the Great Debate, it's the Great Debates.
Right.
Because every time they solve one debate, it opens another one.
Such is the nature of science.
Such is the nature. As soon as you solve something, something else comes along, and you need to solve that.
Yeah.
And of course, astronomy is no different from any other strand of science. And the actual what they describe as the Great Debate was also called the Shapley-Curtis debate. It was held on 26th of April 1920 at the Smithsonian Museum of Natural History between the astronomers Harlow Shapley and Herbert Curtis.
Right.
It concerned the nature of so-called spiral nebulae and the size of the universe.
Right.
Shapley believed that distant nebulae were relatively small and lay within the outskirts of Earth's home galaxy, while Curtis held that they were in fact independent galaxies, implying that they were exceedingly large and distant.
Sure.
We have mentioned this before. That,
yes, indeed.
Before
in connection with Hubble's work and those of others.
That's right. That this is what it was believed, that everything that we saw, if they were fuzzy, they were nebulae. The two scientists first presented independent technical papers about the scale of the universe during the day, and then took part in a joint discussion that evening. Much of the lore surrounding the Great Debate grew out of two papers published by Shapley and by Curtis in the May 1921 issue of the Bulletin of the National Research Council. The published papers each included counter-arguments to the position advocated by the other scientists at the 1920 meeting. So I'll just quickly run into what the actual arguments consisted of. As I said, Shapley was arguing in favor of the Milky Way was the entirety of the universe. So basically, the universe was the main man.
Yeah,
there was nothing else outside it. He believed that the spiral nebulae, such as Andromeda, were simply part of the Milky Way. He could back up this claim by citing relative sizes if Andromeda were not part of the Milky Way galaxy. Then its distance must have been on the order of 10 to the power of 8 light years, a span almost contemporary astronomers would not accept. Adrian von Mon was also providing evidence to Shapley's argument. Von Mon, fan man, was well respected astronomer of the time, who claimed he had observed the pinwheel galaxy rotating.
Okay. Gosh.
Yeah, well, there you go.
Good eyes.
If the pinwheel galaxy were in fact a distant galaxy and could be observed to be rotating on the timescale of years, its orbital velocity would be enormous, and there would clearly be a violation of the universal speed limit, the speed of light. Shapley also backed up his claim with the observation of a nova in Andromeda Nebula that had briefly outshone the entire nebula, consisting seemingly impossible output of energy, where Andromeda, in fact, a separate galaxy. Curtis, on the other hand, contended that Andromeda and other nebulae were separate galaxies, or island universes, as they were termed at the time.
That's right.
In fact, it was a term coined by Immanuel Kant in the 18th century.
Oh, nice.
And he also believed that the spiral nebulae were extragalactic. So he believed that the galaxies were galaxy islands of their star islands of their own. He showed there were more nova in Andromeda than in the Milky Way. From this, he could ask why there were more nova in one small section of the galaxy than in the other sections of the galaxy, if Andromeda were not a separate galaxy, but simply a nebula within the Earth's galaxy. This led to supporting Andromeda as a separate galaxy with its own signature age and rate of nova occurrences. He also cited dark lanes present in other galaxies, similar to the dust clouds found in the Earth's own galaxy. So that was basically what they were talking about. Nice. And of course, then, we went on. So that was 1920. But later in the 20s, Edwin Hubble showed that Andromeda was far outside the Milky Way by measuring Cepheid variable stars, proving that Curtis was correct. It is now known that the Milky Way is only one of as many as an estimated 2 billion or 2 trillion or more galaxies, proving Curtis the more accurate party in the debate. So, yeah, that was originally the Great Debate. So now they've had to accept that what they believe were nebula. Of course, if you remember the Charles Messier catalogue, that all everything's mentioned as nebula, not as galaxies.
That's true.
So it was not until the 1920s with this debate that they decided, and then confirmation by Hubble later in the 20s, that the spiral nebulae, as they called them, were actually separate galaxies. So that settled one debate.
Mm-hmm.
But of course, then moved us on to the second debate. One that we've mentioned before, and it concerned Fred Hoyle and Mr. Einstein.
Aha.
And we are talking about the static state universe or an expanding universe. Well, of course, when Mr. Hubble did his observations and discovered that the spiral nebula were galaxies in their own right, he also found out that the galaxies are moving away from us.
Yes.
The closer they are, they move away at a set speed. You double that distance to the next galaxy and it's moving away twice as fast.
Yes.
And this became known as sort of like the Hubble, part of the Hubble constant. Was it? No, not the Hubble constant. What was it?
Hubble law.
Hubble law, sorry.
Yes.
Which I'll come on. There's another little debate about that. We'll do that in just a second. But he, of course, then, so basically what he said, the further away the galaxy, the further away, the faster it was moving away from us. So the universe was expanding.
Right.
Well, of course, Mr. Einstein, when he did his all his calculations and he gave us relativity and all that, he also found that when he put it all together, again, that's actually dictated that the universe was not static. It was that everything was expanding. But he didn't believe that.
No.
He thought everything was static. What we mean by static is the universe is the same as it was in the past, the same as it will be in the new in the future, and nothing will change. And just all that will happen is the space and the matter will be developed, and then will form more of the galaxy. So he put in, was it called the universal constant or something like that?
It's just called the Einstein's constant.
The Einstein constant,
yeah.
Which basically resolved the matter and it kept everything in a static state.
Yeah, he called it the cosmological constant.
Cosmological constant. That's right. Sorry, I do apologize. So that should come under C. Right. But he put that into his equations. Well, there was a priest called Mr. Lemaitre.
Georges Lemaitre, yes.
Georges Lemaitre, who, using Einstein's own equations, came to the same conclusion that the universe was expanding. But he was a bit shy about announcing anything without actually speaking to Mr. Einstein. So he cornered Mr. Einstein, I think it was in Paris, while there was a great meeting going on, in a park, and he sat down and convinced him to read his research. Einstein said, okay, then I'll read it. He read it, and his basically what he said was, your physics is amazing and outstanding, but your conclusions are absolutely wrong.
Yes.
So he shot this Belgian priest, Mr. Lemaitre, down in flames. But of course, when Mr. Hubble announced and proved that the universe is expanding, Mr. Einstein had to eat his own words.
He had to backpedal a bit.
He had to backpedal a long way.
Yes.
And of course, he removed his cosmological constant, and because then that would allow in his equation the universe to expand as it has done, and he actually called it his greatest blunder.
Yes, indeed.
And with the way things are going at the moment, we may have to reinstate.
Yes, because the elusive dark energy, which is for some reason causing the expansion of the universe to accelerate, behaves very much like Einstein's cosmological constant. And that is really strange. It's got the same sort of properties as Einstein fudged, if you like, made up, if you like, for his cosmological constant. It was the only time, really, when Einstein did something like that. He didn't, he wasn't at that point being a true scientist. He didn't like the result of his calculations. Yeah. So he invented a mathematical trick that would prove himself right, rather than just follow what the observations were saying.
He was basically ignoring the evidence, and
yes,
he was
which of course no scientist should ever do. You go where the observations take you, and if they disagree with what you think, tough luck, basically.
Tough luck, yeah. You've got to find out why they disagree, and
absolutely.
Which again, so now we've got to the stage where we've agreed that spiral nebula are galaxies of their own right. These galaxies are moving away from us, proving that the second debate, which was whether it's static or whether or not it's expanding, as we've moved on to that, which then also brings us on, as you mentioned, dark energy and dark matter things, or dark things, let's put it this way, things that we basically, anything with
things
dark
of the night.
Yes, things that is basically physicists say, we don't know, so let's call it dark. They do use other words like singularity and Big Bang and things like that, which are sort of misnomers. But it brings me on to the last debate that seems to be, which is running currently. And I know we have discussed it before, which is MOND, which is
modified Newton dynamics.
Yes. Dynamics.
Yes.
And this is trying to explain away dark matter. And what they're trying to do is, by adjusting and adding new values to Mr. Newton's equations, which gave us our law of gravity, they're trying to explain away dark matter.
Yes.
And by doing this, I mean, I've said before, to me, it's a bit like a politician adjusting statistics to fit his argument. And to be honest, I think I told Andy earlier, I tried to listen to Mr. Physicist Mordella Milgrom,
oh yes,
physicist. I was listening to him last Friday try and explain his modified dynamics, Newtonian dynamics, and he completely lost me.
What a surprise!
Yeah,
no reflection on you, but you know these.
No. I don't talk Italian.
These people tend to aim for an audience, which is a very select group of people who can understand what the hell they're talking about.
And the maths and the equations he was using were beyond me anyway. But also, he had a very strong Italian accent. There was some background noise, and the sound quality was very poor. So in the end, I gave up, and I'll watch it on the place if I can get it. But the idea is that by adjusting this, they can get away. They can throw away the idea of dark matter, and also then it will help us to explain everything that's going on. Because usually with the dark matter, when we're talking about dark matter, we're talking about star motions in galaxies. When they looked at the rotation of the stars in the galaxies, as we all know, if you say like in our solar system, you've got the sun, then you've got Venus. Well, Venus has to stop actually being pulled into the sun, has to move quite fast in a fast orbit to keep its motion, going, so that it doesn't fall into and it can maintain its orbit and not fall into the sun. Well, the further away you go, you don't have to move so fast to maintain your orbit. You can move at a slower pace, but you're traveling a lot further. And they assumed that it would be the same if you looked at galaxies. The further out from the center of the galaxy the star was, it should be moving slower. But when they measured them, they found that the stars are moving at literally the same rate as the stars in the center of the galaxy.
Yes, indeed they are.
In fact, some of them were even moving faster.
Yeah,
which completely threw them. And again, this is why they come up with, well, there must be more mass than we can actually see. We can't see it, we can't detect it, so it must be dark matter. And using the modified equations, they think that they can actually do away with dark matter and explain what's going on. The only problem is that once they go on to galaxy clusters, which has the same problem, they find that things start to break down. They're not. So, as I said, this is a debate that is going on this very minute. It's got lots of critics. you've got your stalwarts that mean you say you cannot mess with Newton's laws of gravity, and you've got the other people saying this is Mond, we can manipulate the figures to make it do what we say. And doesn't that sound familiar to Mr. Einstein putting in his
absolutely
constant? So
there is though a third way. It's not really an either or, and the third way basically says that Mond may work on some scales and dark matter works on other scales, and it's a continuum. There's no distinction between the two. Some behavior we can attribute to Mond, some to dark matter. They're not necessarily mutually exclusive, which is quite interesting. I'll give you a link, Daz, to a video I was watching about this on YouTube by a physicist, and she explains everything so well. That guy you were listening to, forget him by the sound of it.
Well, this is the bloke who actually formulated the Mond.
Yeah, thing, well, so, just because you can formulate something doesn't mean you're a great communicator.
He created it in 1982 and he published it. Oh, sorry, I called him Italian. He's Israeli, sorry.
Oh,
close enough. 1982 and 1983 he came up with this, and he's still batting for that team now.
Right. So, yeah, there's a German physicist on YouTube. She has her own channel where she explains everything so well. And there's a lovely video on dark matter against Mond, and that's what she was saying, that it could be a continuum, that we see dark matter working at some scales, but Mond working at others.
Oh, okay, then.
I'm not sure there's any explanation as to why that should be, but it could be that they're not necessarily mutually exclusive.
Well, it's another theory, isn't it? And this is what it's all about. Do
you want to hear something really interesting I was reading about dark matter this week?
Go on then.
Go on. This is quite interesting. Supermassive black holes. We know that they existed just a few 100 million years after the Big Bang, and the question is how. How did they grow that massive with masses of millions of stars like our sun so early in the history of the universe? Well, obviously they couldn't have grown through the normal route of black holes when a supernova explodes and contracts, or the core of the star contracts into a black hole. There wasn't enough time for that. So how on earth did these black holes form? And there's a new idea that they actually formed from clouds, if you like, of dark matter that spontaneously collapsed.
Oh, okay then.
And they became the seeds of the black holes. Because as we know, if you take anything and compress it enough, you can get a black hole.
Yeah.
If you wanted to make a black hole out of the Earth, for example, all you'd need to do is compress the Earth to the size of a marble, and then you would have a black hole. Easy, eh? So
project for this week.
So this is quite interesting. But there was a problem with the idea, and that is, if you think of an ice skater spinning on the ice, as she pulls her arms in, she spins faster and faster. This would happen with a collapsing cloud of dark matter, because it's all to do with preservation of angular momentum.
Yeah.
Yes. So when the skater pulls her arms in, because she is effectively smaller, to compensate for that, she spins faster. Now, what they say about the supermassive black holes is that the dark matter pulled ordinary baryonic matter in with it, and without that, the mass would have spun so fast it would have basically tore itself apart, you see.
Right, okay, then.
So it would have been spinning so fast that it would literally have dissipated, torn itself apart. But the normal matter stopped this from happening, so that the cloud of dark matter collapsed into a black hole, spinning very fast, but not fast enough to tear itself apart.
Okay,
and they say that this would explain how black holes grew so early in the universe, and a lot of other things about them as well. So this is a new theory about...
There is the debate whether or not the black hole came first and then the galaxies formed around them, or was it, the galaxy formed, the stars formed the galaxy and then the black hole came later. It's a debate. They're hoping that James Webb will be able to give them some indication of what.
Yes, absolutely.
Because they were talking about micro black holes as well. Which
yeah, I think we can forget those because they're purely theoretical and there's no observational evidence for them. 5
seconds anyway. So.
No, exactly. Also about this, I think this debate, this chicken and egg debate about black holes and galaxies, which came first, I think the general consensus is now, from something else I was reading recently, but I can't quite remember what, that they co-evolved at the same time.
Yeah.
It wasn't the case the black hole was there first and the galaxy followed, or the galaxy was there first and then the center, the mass at the center of it collapsed to form a black hole. It's the fact that they grew together at the same time. So I think that's what the latest idea is, although it's a bit short on observational evidence at the moment. But there's a lot of theoretical work that's been done on this that seems to indicate that the galaxies and the black holes at their centers co-evolve at the same time.
Yeah. Which would make sense, to be quite honest.
Well, of course it would. It seems a bit strange. Anyway, going back to this, back to the original first great debate.
Oh, yeah, back in 1920. Yep.
Back in 1920, it seems amazing to me that they could have thought that the Milky Way was everything in the universe, that there was nothing outside it. Because this smacks of human vanity, doesn't it? Again, thinking that we are in some way in a special place in the universe, and this goes back, into antiquity when we thought that the Earth was the center of the universe, and it was the most important thing in the universe. And then, following that through to think that our galaxy is in any way special, because they knew that. They had an idea that we do live in a galaxy, and they were looking at other galaxies. Admittedly, we didn't know much about the structure of the Milky Way then, not compared to what we do now. But to think that our galaxy and therefore us are in any way special in the universe, I find that amazing.
Well, yeah, as you said, going back to the ancient times, it was believed that the sun was the center of the universe, of the solar system. And it is the center of the Earth. Sorry,
I know what you mean. It's okay.
I just stated the obvious.
Yeah.
What a numpty. Never mind. There you go. But the Earth was actually the center of the solar system. And again, and it also to actually declare otherwise was heretical.
Well, because a lot of this goes back to belief systems, doesn't it?
Exactly, because we've, like you were saying, going back to the 1920s and just prior to that, a lot of people were very, very religious, and it was heretical to mention. I mean, look at the likes of Darwin, the trouble he had with his evolution of species.
Yes, indeed.
Survival of the fittest, etc.
But there are still people today, though, Daz, who believe that we hold a privileged position in the universe. Okay, looking at it one way, you can say that we do because we're the only life that we know of. Exactly. And for the moment, we are in a privileged position. That cannot be denied because we're the only life we know of. But we know that, virtually every star has got planets around it now, and it's unthinkable to think that there isn't life out there.
I think even just in this series of programs alone, we've proved that there's got to be some sort of...
Well, of course.
I mean, if you've got microbial life, then somewhere else it's got to have developed somewhere else. And
but I do know somebody personally who believes he's very religious. And he believes that, God created the universe solely for humans. And he says SETI is a complete waste of money because there's no life anywhere in the universe, that God created the whole universe for us. And, you've got to have really some sort of an ego to think that you're that special, that you're the most important thing in the universe.
Are you saying he got it right the first time?
Yeah, absolutely. Yeah, so this is human ego thinking that we are in any way, in a privileged position in the universe, apart from the obvious one that we're the only life that we know of at the moment.
We're the only example that we know.
Yeah, we're the only example. So
we are arrogant enough to assume that we know what other intelligent life forces are going to be like.
Absolutely.
We put our own values. We think they're going to understand the same physics, the same understand the same philosophies and things like that. But you know, they probably don't even give a monkeys about what anybody else thinks. I mean, they
no, quite.
It's just we are very arrogant in that.
Oh, absolutely. Well, you know, thankfully, because you know, organized religions are dying out. Hopefully, that nonsense will die out in time, and humans will really start to appreciate their real place in the universe. Carl Sagan called it the cosmic perspective, and he said, you know, you'll be lucky to find one person in 10,000 that truly appreciates our position in the universe.
Yeah. I mean, with creationism stories from past civilizations and things like that, it always starts with some sort of deity, which is in a human figure. Although there are some that creatures are involved with some.
Well, as we were saying, a lot of them start with eggs.
Yeah, with real obscure things that happen to them, but then eventually you end up with man. Because there's one we may touch on a bit later on, these G's and that, but the whole belief system, they can coexist if people are open-minded, but unfortunately some of them, you said, have become very zealot about it and want to be really I mean, it becomes belief systems for them.
Absolutely.
Some of them are sort of like because of insecurities, I would say.
Well, no, it's not just that so much. I think it's conditioning by your culture, isn't it?
Well, yeah, exactly.
For example, if we stop telling kids that there was a God, religion would die in the next generation.
Yeah.
It's that simple. It's conditioning by your parents, by your elders, by your priests, your religious people. It's, in my opinion, it's just conditioning. And if we stop telling children about deities, then the idea of a deity would die out virtually overnight. It's a simple fact.
And also, I mean, I don't want to go too far down the religion route and all that, but they can be divisive.
Yeah, absolutely. And we should make it clear we're not singling out any particular religion here. Just the idea of belief systems.
Only flat earthers.
Only flat earthers. Yeah, we'll have a go at them because they deserve it. So anyway, so
that was G for the great debate. We moved a long way beyond that.
Yes, absolutely.
But as I said, basically, one debate led into another debate, and they all have to be resolved before you can move on to the next one.
No,
and in the sidelines, you've got other little squabbles going on as well. So.
I wonder, just out of interest, what the next great debate will be about. That'll be interesting.
Oh, I don't know.
Yeah. We don't know at the moment. It's probably something that we will never have thought of.
No. Like I say, some will come along, and I mean, if they answer the question, if MOND works and all that, there'll still be people who won't let it go.
No, absolutely. But I will send you the link to that video.
Yeah, please do. I appreciate that. Anyway,
so it's interesting. We've been talking about galaxies and galaxy clusters. Because you started with G for the great debates, and my first one is another great beginning with G, not the great debates, but the great attractor. Now, interesting, because first of all, I should say I'm saying the two words great attractor. I'm not saying great attractor as in some sort of superior farm machinery.
Yeah, Ferguson.
Massey Ferguson. Other tractors are available. So
John Deere.
John Deere, that's right. So the great attractor. What is the great attractor? The great attractor is what astronomers call a gravitational anomaly. And it appears to be pulling the Milky Way and all of the companion galaxies in the local group towards a specific point in the sky. So in other words, it's a lot of mass, perhaps millions of times more mass than the Milky Way, acting as a sort of a magnet across intergalactic space. Now, just a bit of history about this. There were first sort of indications that something was going on in 1973 and again in 1978, when astronomers pretty much came to the conclusion that basically the Milky Way and the local group, the 20 or so galaxies that are in our little, I say little, a little inverted commas group of galaxies, was moving not where you think it would be. It's moving in a particular direction as if being pulled by something. And I think that was when I first heard of it, round about the end of the 70s. Now, in 1986, they managed, or say they astronomers who were working on it, managed to pin down exactly where it is. And it's at the gravitational center of a galaxy supercluster, which is known as the Laniakea supercluster. Now, just for the benefit of listeners who may not know the hierarchy, so we have our galaxy, the Milky Way, which is one of about 20 galaxies in a little group. And please, again, the word little is you know, astronomically little, called the local group. When you get a few local groups together, they form a cluster. And when you get several clusters together, they form a supercluster. So this is a hierarchy, if you like. Now, this is all purely arbitrary, but this is, you know, this is how astronomers classify different sizes of collections of galaxies: groups, clusters, superclusters. Now, the Laniakea supercluster contains other superclusters. So if you like, it's a supercluster. It contains the Virgo supercluster. The Virgo supercluster contains the Virgo group, which we know as astronomers is a wonderful region to investigate astronomically, because there are just so many beautiful galaxies there, aren't there?
Galaxies, yeah, the trio and the, what's it, the McKitchen's chain?
Yes, that's right. It's
a
lovely, the Virgo group of galaxies is well worth investigating. You need a decent telescope. But if you have one, then, you know, the Virgo group is wonderful to investigate. Also, the Laniakea supercluster incorporates the Hydra Centaurus supercluster. It also incorporates obviously the Great Attractor, which is, we think, at the gravitational center of the Laniakea supercluster. The Antlia Wall, known as the Hydra supercluster, the Centaurus supercluster, the Pavo-Indus supercluster, the Southern supercluster, including the Fornax cluster, and the two clouds that we know as the Dorado and Eridanus clouds. And all of these make up the Laniakea supercluster. But something at the center of that supercluster, containing, you know, an unbelievable amount of mass that is totally invisible to us, is pulling our local group towards it. Or so we thought. It lies at a distance of between 150 and 250 million light years, the Great Attractor. We can't see very much about what's going on because it lies in a zone which astronomically is called the zone of avoidance. I feel like there should be a big reverb on that voice. The zone of avoidance. The zone of avoidance.
Yeah. The zone of avoidance.
Yeah. Do you know where the zone of avoidance is, Daz?
It's left of the Milky Way, isn't it?
Yeah, that's right. Enough of it. Yeah. The zone of avoidance is along the plane of the Milky Way. We can't see it because the Milky Way, we're looking directly along the plane of the Milky Way, and it's more or less invisible to us because we've got the plane of the Milky Way in the foreground. So it blocks our view of the Laniakea supercluster. So this was the case until 1992. There was no explanation for what the Great Attractor is, exactly how much mass it contained, what it could possibly be. Now, when we talk about massive amounts of mass in the universe, you know, supermassive black holes spring to mind. Perhaps this was actually some sort of cluster of supermassive black holes acting as one gravitationally, but there would have to be, you know, frankly, an unrealistic number of supermassive black holes in one place for that to add up to the gravity that you need, even if they were billions of times the mass of our sun. And so it went on until 1992, when there was an X-ray study of that region of the sky. And the scientists came to the conclusion that it was all nonsense. That in fact, the Laniakea super attractor contains maybe only 10% of the mass that had been measured previously. So the initial figure wasn't correct. This is not to say that the local group is not being pulled in that direction, because it is, but funnily enough, not towards the center of the Laniakea supercluster, but by something beyond it.
Beyond it, yeah.
Called the Shapley attractor, because it lies in the Shapley supercluster, which is beyond the Laniakea supercluster of galaxies.
Is that the Mr. Shapley we were talking about earlier?
It was indeed so, the very same. Harlow Shapley, the very Geller. So there's something beyond the Laniakea supercluster, which only has 10% of the mass of the originally estimated great attractor, but it lays well beyond the Laniakea supercluster. It's in another supercluster of galaxies. So, we are talking many, many hundreds of millions of light years away.
Yeah.
But it still has enough mass. We are undoubtedly being pulled in that direction.
Pulled, yeah.
And there we leave the story, because after that, nobody really knows.
Yeah, because if I remember rightly, this is what was described as dark flow.
Yes, indeed.
That everything is flowing in the same direction, even though we're being attracted to other superclusters.
Yes.
And all these, like I say, these superclusters are all moving in the same direction.
I mean, dark flow makes it sound really mysterious.
Exactly. Well,
like dark energy and dark matter, but all it means is the galaxy is not going where you thought it would.
Yeah.
But it's called dark flow. That sounds very much to me like a ploy to sell books.
It probably was. It was in I think where I saw it was on a documentary, where it was explaining the universe.
Yeah.
They explained, so they went from the Big Bang and all the way up through, and they mentioned dark matter and dark energy, and then they come onto this dark flow, and the punchline was, or maybe it's all wrong.
Yes.
So what was the point of that last hour?
Yeah. Dark flow probably looks good on a book cover.
Yeah,
the mystery of dark flow.
Because I haven't heard of it, and when I've asked people about it, a lot of people don't.
I'd heard of dark flow.
It wasn't.
In fact, I remember having a conversation with a guy a few years ago who got hung up on this idea of dark flow as if it were something magical and mysterious. And I just said, look, instead of dark flow, just call it unusual flow. Because that's all it is,
Yeah, you're just following a stream of a river, aren't we? Really?
Absolutely.
Over anything,
but to cut a long story short, we don't know what exactly the great attractor is, or we should now call it the Shapley attractor rather than the great attractor, just to distinguish it. But anyway, hopefully, future observations will give us some idea.
Yeah, I think that's amazing, actually, with Mr. Shapley. That leads on rather nicely.
Yeah, absolutely.
Do you know how the Galilean moons got their name?
Right, this has to be a trick question. Go on, I'll play. Because they were discovered by Galileo Galilei.
No, what I mean is their actual moon names.
Oh, right. I see. Okay. Right. So we've got the four brightest moons around Jupiter: Io, Callisto, Europa, and Ganymede. Correct?
That's right. That's the chappies.
Right. So these would be based on it's not. They're not Greek. Callisto. Not Shakespearean characters, because that's Neptune. Go on, tell me.
Right, okay then. What I'll say is naming the Galilean moons. When moons began to be discovered, there was no system for naming them. So the International Astronomical Union didn't actually exist then, the ones who interfere in everything. Galileo gave his 4 moons of Jupiter once, because he was the first to observe them.
Yes.
Actually, that's debatable, but we'll move on.
I know there's some debate about that, but let's just take that as read for now.
So we'll take that as read, because they call them the Galilean moons, the 4 big ones. Galileo gave his 4 big moons of Jupiter the collective name Medici Sidera, the Medicean stars, right? After the family of his patron Cosimo de' Medici.
Yes, yes. I was going to say the Medici family were hugely wealthy.
Yeah, exactly.
And
yeah,
you know, basically gave him the money to do whatever he wanted. And that was how science worked in the Renaissance.
That's right. Yeah, you had to have a patron. Yeah,
you had to have patrons. You know,
yeah.
And if you didn't have a patron, you didn't stand any chance of getting scientific equipment or anything. You had to be sponsored by your patron.
Yeah, they probably sponsored the fact that he made because Galileo mainly went into making telescopes. That was his main,
that's right. That's
thing.
right.
So, he didn't discover them. Let's get that right. He didn't discover them, but he did become an amazing telescope manufacturer.
But I think I read somewhere that what was the name of the guy, the Medici? What was his name again?
Cosimo.
That's right, Cosimo. I think I remember reading somewhere that Cosimo liked Galileo because Galileo was outspoken and didn't suffer fools badly.
Okay. Well, yeah,
and Cosimo admired that, so that could be why he coughed up with the dosh.
Yeah, so, that could come up later.
Oh, right, okay.
He distinguished Galileo distinguished them individually by giving them Roman numerals. So that was I, IV.
Right.
So that's 1, 2, 3, 4.
Yeah, I know. You know, I did go to school, you know.
Yeah, well, you're probably using Roman numerals in your maths.
You could. You're the same age as me.
Drop mic. Boom. Working outwards from Jupiter. So it was 1, 2, 3, 4. Now, it was in 1614 that Simon Maurice, or Marius, proposed the names Io, Europa, Ganymede, and Callisto, which were, you were trying to work it out, were some of the lovers of the god Zeus.
So I was right. Was Greek. Yeah.
Yeah, the Greek equivalent of Jupiter.
Right.
Galileo, perhaps aggrieved by Maurice's rival claim to discovery, would have nothing to do with those names. But they did eventually become officially recognized as names that we use today. Though a system of Roman numerals continues in parallel use, no newer discoveries as well. For newer discoveries as well. So they still count in Roman numerals. However, Galileo is honored too because as a group of 4 moons that he discovered, which are much larger than any of Jupiter's other moons, are called the Galilean moons.
Galilean moons.
Yeah. So they're named after lovers of Zeus in Greek mythology. And they were named by a chap, Simon Maurice, who basically put Galileo's nose out by naming them. I don't think I'm not sure whether he actually did declare that he'd discovered them, but there is a debate prior to Galileo seeing them.
Right. Interesting. No, thank you. Yeah.
That was a very short one. I just thought.
Yeah. So therefore, the innermost 4 brightest moons of Jupiter, the Galilean moons, are from Greek mythology again.
Yeah, and of course we know Mr. Europa is or Miss Europa. Corey, she's a female.
Yes, absolutely.
It's very important to us, or could be.
Yes, absolutely. Europa being one of the most promising places in the solar system where we think life may exist, along with Enceladus around Saturn, which in recent years have become the 2 most promising places in the solar system where there might be life. But then again, we talk about the Galilean moons. We've mentioned this before, that they've all got underground oceans.
Yeah. Well, except for Io.
Except for Io, which does have an underground ocean, but it's magma, not water.
It's magma, exactly.
Yeah. So it has an ocean of magma, which I don't think you'll find much life in, to be honest.
The most volcanic active place in the solar system.
Absolutely.
Looks like a pizza close up. So
it does.
With, olives and dotted all.
And it's constantly resurfacing itself. Its surface is so young because it's basically turning itself inside out all the time.
Yeah.
And amazing moon, amazing. So there we are. Well, that was good, interesting. So
Galilean moons. G was for the Galilean.
Yeah. Okay. Right, we're going to move away from the solar system now, and we're going to move to the outskirts of galaxies, where you will find G is for globular cluster. So,
oh, that's one of mine.
Oh no. Okay. Well, we can talk about this. I'm sure you'll have found out some things that I didn't know. Tell you what I knew about them, because I wrote an article for earthsky.org called "What is a Globular Cluster?" I do articles for earthsky.org, which are always what is. It's sort of astronomy basics. So I wrote quite a long article about the basics of globular clusters. So if you can imagine the shape of the Milky Way, which is, if you like, 2 fried eggs back to back, a big bulge in the middle, which not surprisingly is known as the galactic bulge, and then the flat bit, if you like, the plane of the galaxy. But orbiting the Milky Way galaxy, we have these things called globular clusters, which are dense concentrations of stars that in the small telescopes look a bit like fuzzy tennis balls. And they are very densely packed at the center. And at the center of a globular cluster, star densities may be anything from 100 to 1,000 per cubic parsec. And just to remind listeners, if you don't know what a parsec is, it's a distance unit used in astronomy, and it's equivalent to 3.26 light years. So every cubic 3.26 light years, there may be up to 1,000 stars within it, which means the stars are very, very densely packed. Our own Milky Way galaxy has around about 150 globular clusters orbiting the galaxy. Most of them are 10 billion years old or older. In other words, globular clusters consist of very, very ancient stars, second, third generation stars. And they also, because of this, they have low metallicity. In other words, they are primitive stars that really only contain hydrogen, helium, and lithium, because at that point in the universe's history, the generation of stars that went supernova, seeding the universe with elements heavier than hydrogen, helium, and lithium, that point in the universe's history had not yet arrived. So before that point, all you would basically find in the universe would be hydrogen, helium, and lithium, the so-called light elements. And until the first generation had seeded the universe with the heavier elements that they create through nuclear synthesis, and we know about that from Fred Hoyle, who we were discussing last week, the globular clusters are made up of those extremely old stars. And if you can imagine a planet orbiting a star at the center of a globular cluster, it may never get dark. There will be so many stars in the sky that you will never see the night sky. It will be light all the time, which is amazing when you think about it. And in fact, I'm not sure whether I mentioned this before, but Isaac Asimov wrote a famous short story called Nightfall, which takes place on a planet. It didn't necessarily say it was in a globular cluster, but there were multiple stars in the sky. And its orbit meant that night fell only once in a few thousand years. And it's the story of what happens to a society who never see the night sky, who've never seen the universe, when suddenly night falls for the first time and they see the universe in all its glory. And predictably, it sends them mad. And they blame that as some sort of supernatural act conjured up by astronomers. And they start to blame the astronomers for all of the panic and rioting and looting that's going on. People are sent mad because they see the night sky for the first time. And there's a really chilling image from that story, which is a group of townsfolk, if you like, marching on the observatory, carrying flaming brands to tear the observatory down and kill the astronomers who they blame for this. And you know, that image has actually always haunted me, because actually, to be honest, I don't think we're getting too far away from that now, the way that the anti-science movement is going. But Nightfall, short story by Isaac Asimov, well worth a read. So there you are. That's globular clusters, Daz.
Yeah, because what I was on about more was about the age of the stars.
Yeah,
is that they are all formed together.
Yes.
They all vary in size, but they're usually quite big stars, and a lot of them are in pairs as well. So they're in binary systems.
Yeah.
Now, when you look at the Hertzsprung-Russell diagram, and you plot the stars of a globular cluster, they all will sit in if they're still burning in the main sequence, they will sit in the main sequence line, which, if you know the Hertz-Russell diagram,
Yeah, sure.
is the line that goes from top left to
To
bottom
bottom
right.
right. Yeah.
And it's basically stars. It's called the main sequence, and that's stars that are still burning hydrogen quite happily, and that's where they'll spend most of their life.
Yeah.
But because the stars are all formed at the same time and in the same gas cloud, the nursery, they will all sit there on the main sequence. But then when they get the bigger stars, will then start to turn off as they use up their hydrogen and head up towards the red giant stage, which is up in the top right-hand corner.
That's right.
But that point will basically remain in the same place, and it's called the turn-off point. On a globular cluster. And as you said, they're ancient stars, so they'll all be happily going along, and eventually that point will slowly move down and down and down as the smaller stars again tend to go off into the red giant stage.
Yes.
But what they have found, and again this comes back to Mr. Fred Hoyle, that some of the stars remain or look remarkably young. They're bright, they're blue, they're vibrant, and they're burning away.
Yes,
like
I think I was reading about this. Yes.
And they are called blue stragglers.
Yes, of course.
I like to call them vampire stars because, as I said, a lot of these stars are in binary systems. And what basically has happened is you've got two stars, both orbiting each other. And one star, which is probably slightly bigger, has used up its hydrogen and it started to expand. Well, the two stars have been happily orbiting each other, but eventually the expanding star, its atmosphere will breach the barrier of equilibrium.
Right.
That's probably the best way to put it. And then what will happen is the smaller star will start to leach material of the atmosphere off of the bigger star. Now, sometimes, you know, they can cause nova. And if the other star is big enough, the smaller star is big enough, it could even go supernova.
Yes.
But what will happen is these are quite happy to steal all the atmosphere off of the bigger star as it expands in its red giant state. So of course they immediately revitalize themselves just like a vampire does,
and they appear younger.
The blood of us, and they stay young.
Yeah,
and they're burning bright, and they're burning very vibrantly. And as I said, they were called blue stragglers. And it was Fred Hoyle who proposed that there's probably two mechanisms that could cause this. One, that the two stars collide into each other very slowly, not very fast, but very slowly. Or, as I said, the mechanism I've just described, where the smaller star starts to leach the atmosphere off of the bigger star. Right. And this then rejuvenates the younger star, which then burns a lot brighter and then remains. So it appears to be a young star, because they confused astronomers for quite a long while.
That's interesting. How to make yourself stay young forever.
That's right. Yeah, yes. Not become a vampire. No. It's just to, but that's basically what they were called. I like to call them vampire stars, but that's not a technical term. They're officially known as blue stragglers. But as you said, they are all the stars of the same, basically the same age, and they are very, very old. Again, we know that due to their very low metallicity.
Very good.
Yes. Okay. I just thought I'd add that in there for you.
Yeah. Nice one. Nice one.
Right. G is for gold. Right. And it basically is about Ernest Rutherford. As we know, all the elements, excuse me, all the elements are formed in stars. And the heavier metals, i.e. like gold and all that, are usually formed in the supernova, because that's the only places you will find the pressures and the heat hot enough to excite the atoms where they can actually fuse into the heavier elements. So now, as we know, you find gold on the surface of Earth, but that has all come from dying stars that have exploded. A lot of it came to us from the late bombardment, when the Earth was just forming and it was still new, and the Earth's surface was still quite molten, and a lot of it, the gold, has passed through that molten thing and unfortunately, that gold is in the core. So it's all molten and things like that. And people got very excited at a asteroid that they've surveyed called Psyche 16.
Ah, yes.
And
well,
they thought
yes.
that this is a core of a destroyed star, probably due to collisions. All its outer crust has been broken away, and you've just got a solid core of heavy metals.
Yes.
And all that they think it's the core.
Mm-hmm.
And they're talking about that they want to send things up there to mine all this stuff. And they're talking about that the amount of money that could be made on this is absolutely, it's in quadrillions. I think it was something, I think
it's far bigger than the world's economy.
Yeah, so I think it was something like eight quadrillion.
But NASA are indeed sending a mission there in
that's right
23, is it, somewhere around there, I think?
Yeah, but unfortunately they now think it's honeycombed.
Yes, that's right. So it's not solid at all.
They don't think it's solid at all. So
it's still an interesting body to look at, as perhaps the core of a failed planet, if you like. I mean, that will be absolutely unbelievable.
Yeah, exactly. Well, of course, Mr. Rutherford was a physicist in himself, and he was very much into the atom. And I'm trying to find with the actual bit that I'm actually supposed to be reading.
Oh, right.
With his 49th, he struck gold. But it was using it was something to do with using a gold foil. He discovered the makeup. What it was, that's right, he discovered that with the foil he fired electrons or photons or protons or whatever at it, and he found that most of them were passed straight through. Some were deflected at an angle, and some of them
yes, I remember reading about that experiment.
And it was using this gold leaf, very fine gold leaf, that he deduced that an atom is made up of basically space.
Yes, that's right.
And that these small particles that he was firing at them were able to pass between
the atoms of the gold leaf. Yes,
the atoms and the atoms of the gold leaf, and also that they did have a nucleus because of the ones that were being deflected and rebounding back.
Fantastic stuff.
So basically, that's what it was about. I've lost my place in the book, so
don't worry. No, I remember reading about that experiment with the gold leaf.
But I thought it'd be nice to just say that where gold comes from. So when you look at your wedding ring, when you look at any jewelry, gold jewelry, that is where it came from. And of course, we came from stardust as well. So
but more recent thinking says that actually most of the gold in the universe is produced in the collision of neutron stars.
Yeah.
They used to think it was in supernovae, but now they realize that the conditions in a supernovae just don't have the sufficient pressure nor temperature to create something as heavy as gold, and that most of the gold in the universe comes from the collision of two neutron stars, proved in gravitational wave event GW 170817, when in front of their very eyes, astronomers saw something like 500 Earth masses of gold and I think 700 Earth masses of platinum being created through nucleosynthesis in front of their very eyes after these two neutron stars discovered. Amazing.
Yeah, because they were debating, wasn't it? Because you've just reminded me of that, because beforehand they were debating where did all the gold come from?
Because they realized that supernovae weren't up to the job.
Weren't up to it. So, and then of course then they came up with and as you said, with that one you've just come up with.
Brilliant. Well, there we are. So that brings us to the end of another edition of the amazing astronomical alphabet. This has been great fun, Daz. I hope you've enjoyed yourself.
I always enjoy these things. They're good.
Yeah, I think we could have gone for another hour there this week, to be quite honest.
Yeah, well, the one I said at the beginning, there was one that if we did touch on, we could probably do a 2-hour show on itself. And that was actually Mr. Galileo himself.
Mr. Galileo himself.
Everything that's associated
with Galileo. Yes, we could be there for hours talking about.
And there was another one, Gaia, as well.
Oh, Gaia, yes, absolutely. Yeah. The only one I had remaining, which was a very quick one, continuing our tour of solar system moons, Galatea. Fourth closest inner satellite of Neptune. nothing particularly unusual about it, but there we are. Galatea, fourth.
We've got a lot more for the next time, right?
Yeah, we have. Anyway, thank you so much for listening, listeners. We'll be back next week with more from the amazing astronomical alphabet when we reach the unheard of heights of the letter H, if my knowledge of the alphabet is correct. Mind you,
if not, write in.
I did go to school, and I would like to point out to Daz that I did not do my education in Roman numerals, and I always felt sorry. I always felt sorry for that partner of yours, Daz, who did her education in Braille. So,
at least my reading wasn't in hieroglyphs.
Fighting talk. All right, then, listeners, take care of yourselves. Thanks so much for listening. We hope you've enjoyed it. We'll be back next week. So, from Daz,
stay safe, everybody.
Thank you. Stay safe, everybody. Have a great week, and we'll talk to you next week.